All right. 2.1 is patterns in inductive reasoning. It's the first lesson in this chapter. Patterns. Okay. You may not know what inductive reasoning is, but you know what pattern is. You started looking at patterns in kindergarten, in first grade. You looked at blocks. I mean, you started looking at patterns from an early age, shapes, all of that, and you still look at patterns. Now, what we're going to do is we're going to take patterns and turn it into inductive reasoning, which you also do all the time. Okay? We use an example to define inductive reasoning. It says, will your car start tomorrow? Well, if that's the question that you pose to yourself, you start thinking back. Okay? Well, my car has started every single morning since I got it. Okay? So if it started every single day, you can assume that tomorrow morning when you wake up, your car is going to start. Okay? Now, is that always true? No. But you've made the assumption that it will start tomorrow based on a pattern of events that's taken place in the past. That's inductive reasoning. Okay? You use that all the time. Okay? You use it every single day. And yes, it is math. Inductive reasoning is math. Okay? Even though it may not have a number involved, that's math. It's a process of thinking. Okay? A sequence. Okay? A sequence is a shape pattern or number pattern in mathematics. Okay? Or you've heard sequencing of events in English class. Okay? In a story. In a life. Sequence of events. You've heard the word sequence before. This is nothing new. It's just more of a review for you. All right, example 1. What you have is you have a set of rectangles or bricks, whatever you want to call them. Okay? We must first describe the pattern and find the next term in the sequence. All right, when describing something, describing a pattern, describing a picture, you're going to use words. You're basically just going to say what you see, and that's what this is. You're going to write what you see when describing the difference between each pattern. Now, in this first one, I have 4 blocks. Okay. Does anybody else notice anything about these blocks? Yep, they're red. A sequence can be based on colors, a repeating pattern of color arrangement. 1, 2, 1. Does anybody know a mathematical word about that? It's the same on both sides. It was I can see somebody thinking about it. You remember how you used to make hearts in elementary school for Valentine's Day? You used to take a piece of paper. Yeah, symmetry or symmetrical. All right, these bricks are symmetrical. They go 1, 2, 1. It's the same on top and bottom. They're symmetrical. All right. Okay. So, all right, let's look at the next term or the next picture. I go 1, 2, 3, 2, 1. What is the difference between the first picture and the second picture? What have I done to change it? What did you say?
They double. You just put 3. You multiply by 2 on all of them.
Stop shouting out stuff. Y'all realize that all of this right now is being recorded? All this noise, all this nonsense is all being recorded. Quit shouting out answers. I understand you trying. That's great. Raise your hand. All right. What were you saying? Troy, what were you saying? I added a row of 3. So I went from a row of 2 in the middle to a row of 3 in the middle.
Yeah,
You're going to say the same thing? JP, what did you want to say? Multiplied by 2, where? I got 16 here. Okay, so I'm doubling my bricks each time. Okay, what about my symmetrical rows? I went from 1, 2, 3, 4, 3, 2, 1. And I've added a brick. I went from 2 bricks in the middle to 3 bricks in the middle to 4 bricks in the middle, and then symmetrical on both sides. Okay, how would I describe it? There's several patterns here. Okay, I'm going to double the number of bricks. That's one pattern. Another pattern is I'm going to add 1 brick to the middle row. And then fill top and bottom symmetrically. JP, double the number of bricks. Is there a pattern with the colors?
No.
There's no pattern. Now, if it started back over with a red, then yeah, there would be. JP, what did you have to say? Oh, the second one has 9. Oh, so we got to take that one off. So we went from 4 to 9 to 16. Does anybody notice a pattern with the numbers? I went from 4 to 9. What's the difference there? Maybe odd integers? That's something we can test out. Let's go ahead and draw the next. Let's go ahead and draw the next term. All right, I would have how many going across the middle? All right, so I have 5 going across, and then I have 4, and then 3, 2, 1, and I do the same thing going down. So 1, 2, 3, 4, 5, 4, 3, 2, 1. All right, so 1, 2, 3, 4, 5. That's 15. And that would be 7, 9, that's 10. 10 and 15 give me 25. So in my third one, I would get 25. Am I adding 9? Plus 9? So it looks like I'm adding odd integers each time. So there was something with the number of bricks. We just had to find it. So the next one, how many would you add? How many bricks would the next term have? 36. I'd add 11, which would give me 36. All right, so do you see how we can find these patterns and what kind of mindset you have to go into? Looking at numbers, looking at colors, looking at arrangement. Okay, all those things go into numbers and patterns. Okay, that's just called being an observant person. Okay, observe your surroundings, observe situations. That's how you become a problem solver. Okay, observing what's in front of you, what you have. If you're building something, what kind of materials do you have? Okay, putting all those pieces together, trying to decide what you can do with it. All right, B. All right, what we're going to look at here are the white triangles. All right, or the white triangles. How many white triangles do I have in this first one? 1. Now, what did I do to it in the second one? I added 1 triangle inside the white triangle, which gives me how many triangles? 3. Now, what did I do here? I took those 3 white triangles and did what to it? I put a triangle in it. So how many do I have now? 9. Now, my third term, actually, I'm just going to take the term that I already have and add something to it. I'm going to take each white triangle and add a triangle to it. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And how many do I have? How many does the next term have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Oh, I should have colored those in. I'm going to have 27. Multiplying by 3, multiplying by 3, multiplying by 3. What's another way of saying multiplying by 3? It's 3 raised to different powers. But when you multiply by 2 every time, what happens to the numbers? You double it. So when you multiply by 3 each time, you triple. All right, example number 3. All right, example number 3. It's an auto assembly plant can produce a maximum of 300 cars per day. Production line technician observes that during the first 3 hours of a production day, the number of cars coming off the assembly line doubles each hour. Okay, so it's going to double each hour. It says the following table gives a record for the technician's observations. All right, so the first hour, they can produce 10 cars. Second hour, it doubles that 10, and they now have 20 cars. After 3 hours, the 20 cars they had after hour 2 turns into 40. So after 4 hours, how many cars will they have? 80. Now, when running a business, all right, let's push math aside. All right, you're running a business. You have to decide, all right, you got to decide how many people you need to have at work every day. You need to decide how much you can pay them, all right, and how many hours that they can work for this amount of pay, because you have a business to run. A point of a business is to run a profit, all right. So you have to maximize the hours, the amount of production getting done versus the amount of money that you have to spend, either paying employees or paying for materials, so on and so on. This is what business owners do. They look at patterns. Okay, what can I do to keep business up and costs down? Okay, now, do you think that they make a table like this every time? No. Generally, they'll make a table to look at patterns, but then they turn it into basically a formula, not necessarily a mathematical formula, but a formula of how things work. All right. So make a conjecture about the 4th hour. We've done that. Also, let's make one about the 10th hour. Now, we could easily just double this 10 times and figure out the number. Or what happens if the boss's boss comes in and says, I need this amount of cars produced by this day. I don't care if you have to stay longer than 10 hours a day. You have to figure out how long it will take to produce X amount of product. All right, that way you don't overpay somebody or overdo it. So generally they come up with these little formulas to figure things out. Now, we just talked about tripling something, doubling something. 2 to the 0 power equals 1. 2 to the first power equals 2. 2 to the second equals 4. Am I doubling each time? Yes. Now, what am I doing to the exponents? I'm going up by 1 each time. All right, and that keeps going. Now, how can I express 10 in terms of something being doubled? Add a 0 to what? Oh, you're talking about like add a 0 to 1? Yeah, I can add a 0, but think about it in the terms of an operation. How would I take 2 to the 0 which is 1, and turn it into 10? Multiply by 10. All right. So 2 to the 0 power, which is 1, times 10 equals 10, right? All right. How would I get 0 power in terms of my hours? How can I say, all right, 2 raised to the how many powers? Because I'm looking at this based on the number of hours, correct? So if 2 to the 0 is 1, how can I get from 1 hour to 0 to the 0 power? How do I get from 1 to 0? Subtract 1. So let's go ahead and say 2 to the h minus 1 times 10. Everybody see how I've gotten that? How I'm putting that together? Because I can look here too. This is 2 times 10. 2 is 2 to the first power. Well, I can get the first power by doing 2 minus 1. All right, what about 3? That is 2 to the second power, which is 4, times 10, which is 40. So if I come up with an easy solution to find out how many 10 hours can produce, hours minus 1 times 10. Now, 2 to the 10 minus 1 times 10 equals 2 to the 9th times 10. 2 to the 9th power is 520 times 10, which gives me, for 10 hours, I can produce 500, or actually, I think it's 512. Yeah, 1,020 cars. Now, let's say the boss comes in and says, all right, we're going to start working 12-hour days. How many cars can I produce? Is it an easy solution to tell him right now what it is? It is. 12 minus 1 is 11. 2 to the 11th power times 10. All right? There's people doing this all the time. People with college degrees, people with doctorates, people without college degrees are all doing stuff like this right now. I'm going to tell you, I worked at Hibbett's for 4 years in college. I did stuff like this. I wasn't even the manager. I was just an assistant manager. I did stuff like this all the time. Didn't even have a college degree. Just put the patterns together. All right. So this is a good tool for you to have to be productive. All right. Counter example. And example number 4. All right, a counter example. We've been talking about all these patterns and coming up with a conclusion or a conjecture based on patterns. Well, let's just say I flip a coin 100 times and it lands on heads all 100 times. I make the assumption that every time you flip a coin, it lands on heads. Now, is that true?
No.
No. But could it happen?
Yeah.
Yes. Now, what would be a counter example to that? You flip it once and get a tail. That's a counter example. It may work 100 times, but 101st time, it may not work. That's an example of a counter example. Now, it only takes one counter example to disprove a conjecture. Okay? It only takes me flipping that coin one time and getting a tails that disproves my statement that says every time you flip a coin, you get a heads. It only takes one. Now, students in a science class are instructed to sprinkle salt into a Bunsen burner flame. It says each time the salt is sprinkled into the flame turns yellow. It says what conjecture should the class make from their observations? Salt turns the flame yellow. Okay. Now let's say you get a different kind of salt. Okay, you made an assumption that all salt. But now the teacher pulls this out and says, all right, sea salt. Sea salt, you sprinkle it on there and it turns pink. Sea salt turning pink would be a counterexample to the previous statement that says all salt turns flames yellow. Does that make sense? Counterexample. You make an assumption that salt turns the flame yellow. Well, what if a different kind of salt turns another color? You can't make that, so you can't, it disproves the assumption made. Any questions on this? Am I still writing? All right, activity 2. You do not need to write this. You do not need to write the words. You do need to draw the picture. All right, activity 2. We have 3 steps to this activity. Let's go ahead and look at the directions. It says the circles below are divided into regions by connecting points on the circle. In A, 2 points are connected, and the circle is divided into 2 regions. Okay, you can see here that's 1 and 2 regions. B has 3 points, and it's connected, and the circle is divided into 4 regions. 1, 2, 3, 4 separate regions. It says use the points and the regions for the other 3 circles to complete activity 2. All right. Now, what we're looking for is complete the table. So, we're going to count circle C. All right, so we went from having 2 to 4. Now I have 1, 2, 3, 4, 5, 6, 7, 8. So what does it look like I'm doing? I'm doubling each time. Multiply by 2, multiply by 2, so I have 8. Now, the number of points on the circle, what am I doing each time? I'm going up by 1 each time. So I should have 5 and 6. So in D, how many regions should I have? 16. And then I should have 32. All right, so it says before you count the number of regions in D and E, make a conjecture about the number of regions that will be formed in each circle. Okay, complete the table. So we double each time. So we should have 16 and 32. All right. It says what is your conjecture for D and E true? So we made a conjecture that we're doubling each time. What's an easy way to check a conjecture? Why don't we just go up there and count? Let's see, because we guessed 16 and 32, right? Let's go up and count. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Is that correct? We're right by saying that. All right, so we're good there. Conjecture was good. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Were we correct there? No, I did not misdraw it. I'm positive. So, was our conjecture true? No, we needed 32, not 30. Because if not, which circle was your counterexample? Circle E. All right, your homework is page 71. It's 5 through 18 all, and then 20 through 26 even.